All right, so now we'll talk about surfaces. So of course, as the name implies, it's like we're talking about two-dimensional spaces. And in particular, we're going to consider two-dimensional spaces which have the structure of what is called a two-manifold. Okay, so we consider sort of two-dimensional spaces. So in particular, two manifolds. Or surfaces, and in particular, you can also consider them with or without boundary. So what exactly is a two-manifold? Intuitively, a two-manifold is something where everything locally looks like the plane. Okay, so let me try to be a bit more precise about this. So let's look at the idea of topological two manifolds. Okay, so here is that we have talked about this notion of homeomorphisms, which again are continuous maps, which with a continuous inverse, and they're one-to-one and onto. Okay, so so we're going to model it's like these things by the open unit disk. Okay, so let's consider the open unit disk. Okay, so that's just D, which is x in R2 with the property that the norm of x is strictly less than 1. Okay, and you can check that this is homeomorphic to R2. And of course, the easiest way to do this is to exhibit an example of a homeomorphism. Okay. Okay, so let's look at homeomorphism f from D to R2, which is just given by f of x gets mapped to x divided by 1 minus the norm of x. Okay. Okay. So now we want to consider any subset of this topological space that is homeomorphic to the disk as an open disk. Okay. So we call any subset of a topological space that is homeomorphic to D an open disk. Okay, and then with that, you can now talk about what a two manifold is. So a two manifold M without boundary. So we'll talk about the boundary case in a little bit. Okay, but for now, let's look at what happens without boundary. All right, is a topological space where all points lie in open disks. Okay. So all I'm really saying then is that for every point that's like there exists an open disk, it's like which contains that point. Locally like the plane. So if you sort of get close enough to the point, it looks like a plane. Okay. But again, it's like with this caveat that it's only a local thing. Okay, all right. So with that in mind, let's talk about certain properties of manifolds. Okay, just erase everything. Okay, so this manifold M is what is known as compact. Okay, if every covering of M by open sets. So what that just means is that you have a collection of open sets whose union is M. Okay, so that's an open covering. So this is called an open cover. Right, there is a finite subcover. Okay, so again, what that means is that if you give me a covering by open sets of the manifold M, and M is compact, then I can choose some subset of those sets, which still gives me a cover. Okay, and not just any subset, but a subset which has a finite number of terms in it. Okay, or number of elements in it. Okay, all right. So, so this is the idea of compactness. So let me now then say a little bit about what happens with boundary. Okay, so to deal with sort of two manifolds with boundary. Okay, what essentially has to happen is that you have to look at sets which are just morphic to the unit disk, the unit open disk, but also things which are diffeomorphic to the half disk. Right? Sorry, not diffeomorphic, but homeomorphic. Okay, so all right. So we also allow points to lie in sets that are homeomorphic to the half disk. Okay, and the half disk is just D plus. It's just x in R2, again with the property that the norm of x is less than 1, and then the further property that the second component is greater than or equal to 0. Okay, so it looks something like this, right, as part of the x1, x2 components. Okay, all right. And if you recall earlier, I sort of misspoke when I talk about diffeomorphic versus homeomorphic, right? So the notion of homeomorphisms and homeomorphic, it's relevant when one is talking about topological manifolds. Okay, with a topological manifold, you can add additional structure known as a differentiable structure that allows you to talk not just about continuity, but notions of differentiability. Okay, and then it's like if you have maps which are differentiable, then you can talk about diffeomorphisms instead of homeomorphisms. So hopefully that clarifies. It's like what we're talking about. Homeomorphisms are the relevant objects or the relevant relationships between topological manifolds, and then diffeomorphisms are the relevant relationships between differentiable manifolds, where you add a differentiable structure to it. Okay. So that seems like a good time to stop, so I'll stop here for a minute.